This is lecture 3. This is kind of moving away from hardware and memory, blah, 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 into actual computer issues. So this is actually our first introduction to high-level introduction, just to get you a feel for the RISC processor, the RISC order, and assembly language programming in general. So most time when I ask the class, hey, have you ever programmed in assembly language, the answer is no, or maybe one or two people per class. So it's I know it's new to most people. Bad news is it is new. The good news is it's not new in the sense that it's still a programming language. Okay, so that means all the programming constructs and a lot of the skills and the thought processes you gathered from higher programming at a higher level language, you can actually transfer to assembly language. So a computer is essentially a device that reads instructions from memory and executes them on whatever hardware you have. So the ramifications of this are the fact that this computer, this piece of hardware, we'll say, and the instruction set is it was designed by humans. It's completely arbitrary. Don't get the idea that this is amazing, only one way to do it, and you have to do it this way, or you suck or something like that. This is all completely arbitrary. You should keep that in mind no matter what's going on. I mean, I know you have to learn what we are doing, but keep in mind in the big picture, you should be asking yourself, wow, why did we do it this way? Maybe there's a better way to do it. So this computer in general, it executes about 40 instructions. It sounds like a lot, but it's really not a lot of instructions, particularly in assembly language land. There's some processors with like 300 and 400 instructions, so we're not there. Also, the instructions are very similar to each other. It really doesn't do that much. But the good thing is that with these instructions, it's written really generically. You can solve practically any problem without too much trouble. If you don't have the instruction you need, you can always kind of like fake it with the instructions that are available. So this is our computer model. There's 3 basic parts to this, which is memory, I/O, and then you got some kind of central processing unit or processor, I'll say, that crunches the data. So essentially, the memory is doing 2 things. It's reading instruction memory. You can see the instruction memory connected to the control unit, and it's also crunching data. And so that way we got a path between the data memory and the hardware that crunches it. We need to talk to this thing also, so there's typically an I/O unit. So I placed this slide out there because the fact that all the instructions have to do with essentially moving data around these 3 boxes here. I mean, that's really all there is to it. There are only 3 boxes. There's only so many ways you can move data around on this thing. So in the end, it's not overly complicated once you get used to it. So you got a new computer. Essentially, what you need to do is understand all aspects of it. Like I said, you may need to modify or steal it. Every computer has hardware in there, and you think, wow, that's a good idea. I'm going to use that in my computer, etc., etc. So anytime you have a new computer, these are the 5 things you look at. We've looked at a couple of these. We mentioned them before. So essentially, the programmer's model and the instruction set, that's going to come up in the next slide here. But the interrupt architecture, all these devices have the ability to operate in a real-time mode. We'll talk about that later. Memory model, super important. We'll talk about that later also. And we got to be able to talk to this thing. Typically the I/O architecture is important, so you got to know how to talk to it. Okay, so check it out. I used the word architecture about 3 different times there. Kind of an overused word in computer land. So this right here is the instruction set. This is the programming model, the programmer's model. This is the hardware that the programmer has access to or can control, and they control it using the instruction set. So this is, I'm going to pass this by you because Honestly, I know it's out of date. This is old one, but you guys don't know any better right now, so I'm going to go ahead and leave that up there. But some of these instructions have changed. I actually used this last quarter, the beginning of the quarter, before I had a clue what was going on. So once again, this is really important. Here's the instruction set. I use these instructions to control this hardware. This is not all the hardware in the computer. There's a lot more hardware than that. In fact, we'll click to it. This is all the computer hardware there is, which is obviously different than the programming model, but the programmer using instructions doesn't have access to all these modules. So, yep, there it is, instruction set. Controls certain parts of the hardware, etc., etc. We looked at that before. So the instructions themselves are a bunch of bits. So the bits are in the machine code. Essentially, each of the instructions are a bunch of bits. The underlying hardware uses those bits to essentially generate the answer you're hoping for. So we'll comment about complexity and quantity of instructions here. It's always the ultimate trade-off in computer design. If you have many instructions, that seems good because your instruction can do just about anything, but that complicates your hardware. And essentially, the issue here is your computer will be able to do a lot more stuff with a lot less instructions, but the hardware will be more complex. Then, eat more power and all that, and that type of thing. So if you have fewer instructions, generally speaking, the hardware is more simple, but the computer is going to require more instructions to get a certain task done. So this is a RISC processor, reduced instruction set. It is kind of on the simple end of things, which is good because we have to implement these instructions, as you'll see later. This is a reminder of that, the 3 levels of programming. This is the machine code, which is the ones and zeros that essentially control the hardware. Hardware only understands ones and zeros. You've programmed at a higher level language. That higher level language is compiled down to assembly code and later to machine code. We are going to be programming at the assembly language level. So we're going to write assembly language, send it off to the assembler. The assembler is going to generate the machine code and send it off to the computer. So we're in this level right here. So the big picture here, you're going to write a program. Okay, so that's what we're going to do, write a program. Why are you writing a program? Well, for one reason, essentially going to solve a problem. Okay, so to solve that problem, I'm trying to put this into boxes here. You need to understand you need to understand the problem. Then you need to generate some type of solution, and then you're going to translate that solution to assembly language. So the two ways to, I'll say, generate a path to the solution are writing pseudocode and flowcharts. So typically speaking, anytime you write a program, you just don't sit down and write a program. The very first step is to write pseudocode or a flowchart. I will eventually get to flowcharts. Hopefully you had that in your higher level programming language. It's extremely useful in assembly language because so much of what we do is at a low level. Pseudocode works to do whatever you can to keep yourself organized. Assembly language has a tendency to very easily get out of hand, and so you don't want to do that. So keep it simple. Start with a flowchart. I know I always say that, and no one ever does it, but that's what you need to do. So the RISC, we're going to be working with this RISC-V architecture. I'm going to be calling it my MCU, which is microcontroller. But typically we'll sometimes call it Otter, which is the name that Joseph gave it. And so we're working with RISC-V Otter. So it is a really cool architecture. It's open source, which means a lot of people's brain power went into making a cool processor, and it is pretty cool. Keep in mind that the only thing that was specified by this open source architecture is the instruction set. Okay, it's like, here's the instructions. It's up to whoever like us, for example, to generate the hardware to implement those instructions. Okay, so it's not magic. It's very open-ended. Typically, there's many different solutions for this. We've kind of chosen one. It is a general purpose instruction set, meaning there's not that many instructions. Instructions are pretty general, but with those instructions, you could practically solve any problem. Yeah, so the architecture is very simple. The instructions are very simple. Well, you'll see that later, and essentially, it allows us to implement the thing without too much effort, and which is what we'll be doing. And of course, here is the architecture. Looks like a lot, but when you break it down piece by piece, which is kind of what we'll be doing, it's really not too bad.